Alright, let's start this one up. So we're going to pull on our mass, right, 4 kilograms with our certain force. We're going to solve for these values. So the first one is find K, right? So notice if I pull this back this way, what should be true about max force and spring force? They're equal, right? So the spring force should equal the max force. So this should be 20 newtons. Now, it's not exactly equal because your max force is to the right, the spring force is to the left. So if we want to keep this consistent, we'd say, all right, my spring force is negative 20 in the opposite direction. That will equal negative K, and then my distance was 10 centimeters, 0.1 meters. Gives me a 200 Newton per meter K value. Okay, letter B, let's find A if we let go. So we're going to let go of this, which means, what's my F max now? My F applied is 0. So there's only one force, so if we do our FBD, the only force is the spring force pulling to the left. So this will simply be Fx equals ma. Now technically, again, this is to the left, so if we want to stay consistent with their directionality, we'll say that is negative 20 newtons equals our mass of 4 and our A here. So A should be negative 5. Okay, let's just go over some concepts here. When I let go of this, what happens to the A as it starts moving this way? What happens to the acceleration as it heads towards its equilibrium position? Okay. Does the acceleration increase, decrease, or stay the same as it's moving this way? Decreases, right? So as the acceleration, as it moves this way, at the max it's at 5, right? But as it moves this way, what's happening to the force? It's getting smaller, right? The force of the spring is getting weaker as it moves this way. So what should be happening to the acceleration? It's decreasing. Okay? Now does that mean it's slowing down? In fact, what's it doing? Speeding up. Okay? It's just not speeding up as fast. So here at the peak it's 5 meters per second squared, right? But halfway, what would it be halfway? 2.5 meters per second squared. So it's still speeding up, it's just speeding up at a slower rate. And in fact, what's happening at equilibrium point? It has 0 acceleration. So at this point, actually let me just kind of redraw this. This is a big concept, so make sure you understand this. So like way over here, this is my x equals 0. Way over here, this would be, I would have essentially a maximum force. I would also have a maximum acceleration. And as it's moving this direction, its acceleration is decreasing. And in fact, at x equals 0, what is the acceleration? 0. There's no more acceleration at this point. Okay, because there's no more force. That's its normal point when there's no force at all. It's not stretched, it's not compressed. This would be as if F equal to 0 at that point. Okay? Now what is happening to the object as it moves this way? What's happening to its speed? It's speeding up, right? And at this point we would have a maximum velocity. What would be the velocity back here at the edge? 0. Yeah, this would be 0 over here, right? We just let go. It has its initial velocity equal to 0. Now what if I asked you to tell me how fast is it moving after a second? Could you do that? How would we do that? Okay, we actually couldn't do that directly. Okay, you have your kinematic equations, right? However, those only work if what's true? Acceleration is constant, right? If acceleration is the same. And so you can't just blindly plug it into one of these because the acceleration is continually changing as it moves in this direction. And in fact, you could solve, most of you could solve this because you should have done this in calculus. Okay, when you have variable accelerations, you can solve for the, your kinematics using calculus, derivatives, or integrals. All right, so anyways, let's continue this. So we're going to go this way. What happens is it starts moving in this direction. Starts to decelerate, right? So here, it's going to start to decelerate. And what's happening to its acceleration is it goes this way. It increases, okay? The acceleration is going to increase in the negative direction, right? But it's going to get greater and greater and greater till it reaches the end. This would be a max A over here, and F max over here. In fact, this would be symmetrical to the other side, right? Assuming there's no acceleration, assuming there's no friction, the numbers would even be the same. Okay? All right, one last thing. So this would be an X max. X equals 0. This would be an X max. This actually has a name. Our maximum displacement is called the amplitude. Right? And essentially what's happening is this is going to go back and forth. It's going to continually go back and forth. This is called simple harmonic motion as it goes back and forth. And we're going to get into the details of that tomorrow. But just know that it's going to go back and forth, and if there's no friction, this X amplitude would be the same on both sides. Okay, 10 centimeters this way, 10 centimeters this way. So let's get back to the problem. Letter C. How does this change if we add friction? Okay, let's do the FBD now. Where's the force is acting on this object? Okay, we have the spring force still. And then what else? Okay, we have friction. Those are the main ones we need. We have our usual Fn and Fg, but we have Fs and F friction. Actually, I didn't really draw these accurately. How should I draw these? Okay, friction should be smaller, or this should be longer. And when we set up our equations, right, we should have our spring. And actually, if we want to keep our directionality good, we can go F spring plus F friction equals ma. Now if you flip that, that's okay. If you did spring minus friction, that's okay too. So this would be negative 20 plus, what's our equation for friction? Mu times Fn. What's Fn if it's on a flat surface? Mg. Mu mg. This is 0.1 times 4 times 9.8. So it looks like our A is about 4, negative 4, negative 3 point something. Oh, 4.02. Okay, so that would be our acceleration.